Very good morning to all of you. Today I want to start Module 3 of Session 6. Title of Module 3 is Lateral Earth Pressure. The course outcome of lateral earth pressure is ability to compute lateral pressure distribution behind earth retaining structures. Title of subject is Applied Geotechnical Engineering and subject code is 18CV62. It comes in 6th semester of Civil Engineering Department. Next, from the last sessions, now I want to continue these sessions with based on the uniform surcharge pressure, how pressure distribution diagram is plotted. A uniform pressure that is called surcharge is sometimes applied at the top surface of the backfill. For example, it is customary to apply a uniform pressure of 15 to 20 kPa to simulate the effect of traffic loads on a retaining wall. A uniform pressure Q applied at the top surface causes an increase in the at rest lateral earth pressure equal to K0 times Q. Figure 7.6 shows how to account for the surcharge effects for a retaining wall with a dry backfill, a submerged backfill and a partially submerged backfill. So based on these three conditions, if the surcharge load is occurred, then how to plot the lateral pressure distribution diagram? Let us see. See, this is figure 7.6. Here three conditions. One is, so this is retaining wall of height h, water table at the base, and this is the surcharge load acting on the top of the retaining walls. That is surcharge load in kilonewton per meter square. And these are the soil properties, that is backfill properties. Unit weight of soil, angle of internal friction of soil phi, and cohesion of backfill, that is C. In the second case, surcharge load is acting but water table at the top levels, the top surface water table is there. Then here saturated unit weight is considered, but here dry unit weight is considered because water table is bottom. And this condition is third condition, water table is at a depth of h1 and this is h2. So here above the water table backfill property is gamma phi dash c dash. Below water table unit weight of backfill is gamma saturated phi dash c dash. And this is the surcharge load. Based on these three cases, how lateral earth pressure distribution diagram is plotted. See, this is the first diagram with respect to this first case. So this is the surcharge loads pressure distribution diagram, that is rectangles. This from top to bottom. Surcharge load is acting along the height of the retaining wall. So that we are calculating lateral earth pressure, that is sigma h dash, we are calculating K0 into Q. So this is the triangular diagrams. So this pressure distribution equation is K dash times H equal to K0 into Q. And due to backfill, pressure distribution diagram is this is triangular diagrams, that is number 2. Number 2 is pressure distribution diagram with respect to backfills, and this number 1 is pressure distribution diagram due to surcharge load, that is rectangles. But the total pressure distribution diagram we are considering as a sigma dash h equal to this shape pressure plus this diagram pressure. It means we are doing the summation, this plus this, that is K0 into Q plus K0 into H. That is the pressure distribution diagram of this case. And if the this case a water table at the top of the surface. So then see here how to draw the pressure distribution diagram. Number one is rectangular diagram. This is due to K naught into Q, and this number two is pressure distribution diagram with respect to backfill with submerged density, that is K naught into H into gamma saturated minus gamma W. So this pressure, and this third pressure distribution diagram with respect to water, that is water pressure, that is H into gamma W. So then total pressure is, total lateral earth pressure is sigma dash H equal to this plus this plus this, that is K naught into Q plus K naught into H times gamma saturated minus gamma W plus H into gamma W. This is the total lateral earth pressures of these diagrams. And for this case, so this here different heights water table is available. So for H1 height, you draw the pressure distribution diagram. H1 height means here K naught into Q, this is the pressure distribution diagrams. This diagram is with respect to surcharge load, and this second diagram is due to backfill pressure distribution diagrams, number 2. This is due to backfill, that is triangulars. And second, so due to this depth plus this depth, so surcharge load is here K naught into Q plus K naught into H1 into gamma, that is due to H1 and H2 heights, that is pressure distribution diagrams at the depth H2. And this diagram is with respect to H2 depth backfill, this, that is K naught into H2 into submerged density, that is gamma saturated minus gamma W, this. And this diagram is with respect to water pressure, that is H2 into gamma W, because H2 height into unit weight of water, that is H2 into gamma W for this. Okay. So now based on this concept, how to plot the pressure distribution diagram and how to calculate lateral earth pressure for the given height of retaining wall with soil properties, that is most important. See, this is one numerical problems. As shown in figure 7.7a, a 4.5 meter high retaining wall has a sandy backfill with C dash equal to 0, phi dash equal to 37 degree, gamma equal to 17 kilonewton per cubic meter, and gamma saturated equal to 19 kilonewton per cubic meter. The water table is 1.5 meter below the surface of the backfill. Calculate the at rest lateral force exerted on a 1 meter long section of the retaining wall. Assume that the sand below the water table is fully saturated. So this is the problem. Based on the problem, this diagram is there. Okay. H1 is 1.5 meter, H2 is 3 meter, total is 4.5 meter, 8 retaining walls. At a depth of 1.5 meter, water table starts. Above the water table, these are the backfill properties, and below the water table, these are the backfill properties. So this problem is similar to earlier theory class. So now you plot here pressure distribution diagrams with respect to this case. So you draw this retaining wall as usual, okay, and at H1 depth you draw the pressure distribution diagram with respect to backfill. This is triangular, and same pressure is acting here. This is diagram 2, and third diagram is this backfill due to H2 depth of height. This is pressure distribution diagrams. This is third. And fourth one is pressure distribution diagram due to water, that is triangular. Water table is at a depth of H2. So this is the pressure distribution diagrams with respect to H2 depth. Okay, and we are locating here diagram 1 pressure is P1, diagram 2 is this similar same pressure P1, and for this pressure distribution diagram we are locating P2, the total force, and for this force P3 is acting at this CG, and P4 is we are locating the distance of CG. Okay, so now how we want to solve this problem, let us see next step. Solution. Figure 7.7b shows the distribution of the effective lateral earth pressure and the distribution of the pore water pressure against the retaining wall. The coefficient of lateral earth pressure at rest is calculated using Jacobi's equation, that is K0 equal to 1 minus sin phi dash. So substitute value here, 1 minus sin phi dash 37, we are getting 0.4. Thus at Z depth, at Z equal to 0 meter, so then sigma dash H is 0 and U is also 0, water pressure is also 0. At Z equal to 1.5 meter, so then you calculate lateral earth pressure, that is sigma dash H equal to K0 into gamma into H1s. So this is Z equal to 1.5 meter, so that is K0 into gamma into H1s. Okay, so now substitute the value here. K0 is 0.4 into gamma is 17, this gamma is 17, H1 is 1.5, so we are getting 10.2 kilonewton per meter square, and water pressure is 0. At Z equal to 4.5 meter, so the lateral earth pressure sigma dash H equal to this plus this pressure. Okay, see K0 into gamma into H1 plus K0 times density into height, that is gamma saturated minus gamma W into H2. See here, water table is below the 1.5 meter depth, then we are multiplying density in terms of gamma submerged. So that is gamma submerged means gamma saturated minus gamma W into height H2. So now substitute the value here. K0 is 0.4, gamma is 17, H1 is 1.5 plus 0.4 times K0 is 0.4, gamma saturated is 19, gamma W is 9.81, H2 is 3 meter, so we are getting 21.2 kilonewton per meter square. And water pressure U equal to unit weight of water into depth of retaining wall. So here unit weight of water is 9.81 and H2 is 3. So we are getting 29.4 kilonewton per meter square. Next step, the at rest lateral earth pressure diagram is divided into two triangles and one rectangle as indicated in figure 7.7b. The pore water pressure distribution is triangular by nature. The lateral forces P1, P2, P3 and P4 are equal to their respective areas denoted as areas 1, 2, 3 and 4 in the figures. So we are locating the areas of area 1, area 2, area 3, area 4 like that. So now you calculate lateral forces P1 equal to, so here force into distance, that is moments. First you calculate area each say. So P1 equal to half into base into height. Half into base is 10.2, height is 1.5 meters. Okay, half into base into height. So this is area into 1 meter height. So we are getting 7.65 kilonewton for a 1 meter long sections. And next P2, you calculate the area of that diagram, that is B into H, that is second diagram. See, this is breadth into depth. Okay, So that is 10.2 into 3 into 1 meter, that is per meter, 1 meter long sections. So we are getting this much kilonewtons. Okay. And P3, so area, the half into base into height into multiple 1 meter length. So we are calculating 16.5 kilonewtons. P4 equal to, that is area of the triangle, P4. So this P4, area of the triangle is half into base into height. So that is half into base is 29.4, that is this is 29.4, height is 3 meters into 1 meter. The long section we are calculating. So 44.1 kilonewtons. The at rest lateral force is, so therefore P0 equal to P1 plus P2 plus P3 plus P4. So means you do the summation of the total. P0 is total force is acting, then you do this plus this plus this plus this. So same concept we have applied here. So now substitute the value, we are getting P0 is 98.85 kilonewtons. The location of Y of the point of application of the resultant P0 measured from the heel of the retaining wall can be calculated by taking the moment of P0 about the heel and equating that to the sum of the moments of P1, P2, P3 and P4 about the same points. Okay, so means now you take the moment with respect to this diagram. P0 into distance at the heel, this is the heel point, force into distance, this is clockwise, is equal to the summation of all that P1, P2 force with respect to distance. So that we have done here. P0 is 98.85 into distance, force into perpendicular distance, that is P0 into Y is equal to the 7.65 into 3 plus half of the distance. See here, for this P1 into perpendicular distance, so that is 3 plus at a 0.5 meter depth we are considering, that is moment, plus P2 into distance, this P2 into perpendicular distance means half of the CG, that is 1.5 by 2. Okay. Next, P3 into distance, P3 into distance, P3 into distance, that is 1 meter, plus P4 into perpendicular distance, 44 into 1. See here, P4 into perpendicular distance, that is about the base, h by 3, that 3 by 3 means 1 meters. So then finally we are getting Y is 1.35 meters. So means here P0 is acting at a distance of Y, that is Y is 1.35 meter. So this is the complete solution of these problems. Okay. Now you remember here simple steps and how to plot the pressure distribution diagrams and how to resolve, that is the main concept, and how to do the movements, that you should be remembered. So similar type different problems are asked. Okay. Next, active earth pressures. What do you mean by active earth pressure? The active earth pressure is a destabilizing pressure that occurs when the retaining wall is allowed to move away from the retained soils, that is away from the backfills, that is active earth pressure. The active earth pressure condition will develop only if the wall moves a sufficient distance away from the backfill. The lateral outward movement required to mobilize the full active pressure. Condition is approximately 0.001 times H for loose sand and 0.04 times H for soft clay, where H is the height of the wall. The active earth pressure distribution can be calculated using Rankine's theory or Coulomb theory. Let us see what do you mean by Rankine's theory. See these diagrams. Okay, this is base, this is the retaining wall of height H, and this is the top to top retaining wall. This is the backfill, this is the soil element, and this is the active earth pressure, means retaining wall moving away from the backfill, that is active earth pressure. And this is the diagram how active earth pressure is acts. So this is the top surface, these are the failure planes. Okay, this failure plane acting at an angle theta equal to 45 plus 5 by 2. Okay, so this is the concept of how active earth pressure is explained by Rankine's theory. The Rankine's active earth pressure theory assumes that the soil behind a retaining wall is in a condition of incipient failure. Every element within the sliding wedge shown in figure 7.8a is on the verge of failure as depicted by the Morse circle, which is tangent to the Morse Coulomb failure criteria as shown in figure 7.8b. See this is 7.8b. How to plot this Morse circle? So we know, so this is normal stress, this is shear stress based on the sigma 1, sigma 2, or based on the sigma dash h, sigma dash v. We are plotting the Morse circles and we are getting the failure planes. Okay, so this angle is, so here from here to here pole and here to here we are calculating considering distance sigma dash h, and this circle is at rest conditions and this circle is active conditions, and this angle is theta equal to 45 plus 5 by 2, and this is we are locating as a failure plane, and this is the main Morse failure criteria, that is tau f equal to c plus sigma tan phi concepts. Okay, Rankine's active lateral earth pressures. This Morse circle represents the stressed condition in a soil element located at a depth z below the top surface of the backfill. For reference, Morse circle for the at rest condition is also shown in the figure. The at rest stress condition occurs when the wall is stationary. When the wall starts moving away from the backfill, the lateral stress sigma dash h decreases while the vertical stress sigma dash v remains essentially constant. The limiting condition occurs when the Morse Coulomb failure criteria becomes tangent to Morse circle. At each condition, the lateral stress reaches its minimum possible value, termed the active lateral stress, that is sigma dash v. The Morse circle shown in figure 7.88b predicts two sets of failure planes with theta equal to plus or minus 45 plus 5 by 5 dash by 2. These two families of failure planes are also known shown in figure 7.8a and c, that is C here. So this is A and this is A. We have seen the here theta value. Okay. To simplify the analysis, Rankine's theory assumes that there is no adhesion or friction between the wall and the backfill soil. The retaining wall is vertical and the backfill soil has a horizontal surface. So this is the Rankine's assumptions. Okay. To simplify the analysis, Rankine's theory assumes that there is no adhesion or friction between the wall, and the second assumption is the backfill soils. The retaining wall is vertical. The retaining wall is always vertical and the backfill soil has a horizontal surface. This is the assumptions of Rankine's theory. From the limiting failure condition represented by Morse circle shown in figure 7.9, we can write sin phi dash equal to OB by OA, means y by x, OB by OA. So this is sin phi dash equal to OB by OA is equal to sigma dash V minus sigma dash A divided by 2, and OA is C dash cot phi dash plus sigma V plus sigma dash by 2. This is equation 3. After some manipulation of equation 7.3, we can show that sigma dash A is equal to sigma dash V tan square of 45 minus pi by 2 minus 2c times tan of 45 minus pi by 2. This is the simplification. So based on that our equations, we have plotted here more circles based on the value givens. Okay. So this is the most important concept about the explanations of how to plot the Morse failure envelope. Okay. So based on the value, so from the origin we are selecting x distance with this distance, and with this distance we are selecting the radius, and we are locating O point. This is B point, and this is the radius, and we are plotting Morse circle, and we are locating tangent point, and we are this line is perpendicular to this line, and this line we are defining as a Morse Coulomb failure criteria. So this diagram is explanation for active conditions. Okay, and this is Rankine's active lateral earth pressure for a cohesive backfill without surcharge. Okay, Rankine's active. So this is height of the retaining wall, water table at the base. These are the backfill properties. Now here we are plotting the pressure distribution diagram based on the Rankine's lateral active earth pressure. So due to backfill, so this is the triangular. So here this is the K naught into gamma into H, K into gamma into H. Here K is the active earth pressure into height into density of soil. So this is the due to backfill diagram, minus 2c dash root of Ka. So this is due to water tables diagram, minus is equal to active earth pressure backfill. So this is minus, and this is, and this critical depth we are locating at a pressure distribution diagram 2 times c dash root Ka. Okay, so finally we are getting the base pressure is sigma dash A is Ka H gamma minus 2c dash root Ka. This is the Rankine's active lateral earth pressure for a cohesive backfill without surcharge. So these are the references are made for to finish this session 6 with the different authors, textbooks, course I have referred. Okay, thank you one and all. Next class I will be continue.